Hello everyone, my name is Caitlin Fisher. I'm a senior physics major with astronomy minor here at Radford. In summer 2020, I was able to do research thanks to the Office of Undergraduate Research and Scholarship. Throughout the summer, I was mentored by Dr. Liz, who is a professor in the physics department. So our research was on the distribution of stars and interacting dwarf galaxies. So before we talk about dwarf galaxies, what do we know about massive galaxy interactions? When two massive galaxies interact, there's a gravitational pull from one on the other. Throughout this interaction, the galaxies eventually merge into a single massive galaxy that is no longer forming stars. At these low redshift galaxy interactions, many of their properties are affected, including the star formation rates. The astronomy community knows a lot about massive galaxy interactions and mergers. However, extensive studies have not been done on these dwarf galaxy interactions, despite them being the dominating galaxy population in the universe. Therefore, we need to research how these dwarf galaxy interactions to further our understanding on the properties affected throughout the merging sequence. Dwarf galaxies versus massive galaxies. One of the major misconceptions of dwarf galaxies is that people automatically assume they are just scaled-down versions of massive galaxies. This is not true. Many aspects that make up these galaxies differ, such as they have different star formation histories, so dwarf galaxies typically have stars that formed earlier. They have low fractions of metals. Dwarf galaxies are inefficient star formation. They have shallower gravitational potential wells, and they're not scaled-down versions of massive galaxies. So our research was conducted on the information provided by the Tiny Titan survey. What is the Tiny Titan survey? It is the first systematic study of interacting dwarf galaxies. It is the sample of 60 isolated and 44 non-isolated dwarf pairs. They were selected from the Sloan Digital Sky Survey, which contains optical photometry and spectroscopy of galaxies and stars in 1/3 of the sky. They were selected upon specific criteria. For the isolated dwarf galaxy pairs, they must be at a distance that is greater than 1.5 megaparsecs from a massive galaxy that has a mass greater than 5 times 10 to the 9th times the mass of the Sun. These dwarf galaxies must have a redshift that is greater than 0.005, but less than 0.07. These dwarf galaxies must also have a mass that is greater than 10 to the 7 times the mass of the Sun, but less than a mass that is 10 times 10 to the 9th times the mass of the Sun. These dwarf galaxies must also have a radius separation, so the dwarf galaxy pairs must have a separation that is less than 50 kiloparsecs, and they must have a velocity separation that is less than 300 kilometers per second. So isolated versus non-isolated. The isolated dwarf pairs are at a distance that is greater than 1.5 megaparsecs. So they have no external environmental effects from the more massive galaxies. So non-isolated galaxies are within that distance of 1.5 megaparsecs. So they can experience these environmental effects from the massive galaxies. So what are these environmental effects? Well, they include ram pressure stripping. So as these galaxies move towards each other, they have pressure that can push the material that forms stars outwards. There is also tidal forces or other factors that significantly influence the dwarf galaxy evolution. So you can see there's two images on the right. So the top right image shows in the black dots massive galaxies. And the red and orange dots are galaxies that are quenched, so they no longer have this material that forms stars. The blue and green dots represent stars that are dwarf galaxies that do produce stars. So as you can see there, the dwarf galaxies that are closer to those more massive galaxies are typically quenched. The ones that are further away typically still have that material to form stars. So in the bottom right image, you can see that at that about 1.5 megaparsecs, these stars or dwarf galaxies are no longer quenched. So there's typically less quenching after that distance. But beforehand, there's typically a lot more quenching. So research purpose. Our research question that we went off was, how do interactions between dwarf galaxies impact the distribution of their stars? So the goals of this research were to 1. Generate color maps of star distribution from the archival of SDSS data. 2. To perform quantitative and qualitative analysis of age and temperature distributions of galaxy and pair properties. 3. To contextualize results with other astronomical objects. So let's talk about the importance of UGRIS. So what is UGRIS? So These U, G, R, I, Z represent the filters that are used on the SDSS telescope. So for U, which is ultraviolet, it allows a wavelength or around it that is 3,543 angstroms. Green, G, allows in wavelength that is 4,770 wavelength angstroms. Red, R, allows in wavelengths that are 6,231 angstroms. And near infrared lets in 7,625 angstroms. And the infrared range lets in wavelengths that are about 9,134 angstroms. So what does UGRIS tell us? They tell us the temperature and therefore the mass of the stars. So we use the subtraction of UGRIS to determine what the color of the stars are in the dwarf galaxies. So you can see there's an image at the bottom which shows us the range of the colors. So at the 4,000 range you have the ultraviolet and violet, and up at the 7,000 range you have red and near infrared. So the process of our research. So one of the first things we had to do was download the SDSS UGRIS FITS files for each of the 104 dwarf galaxy pairs. So then we had to use Python packages to reproject and subtract the various colors. So at the bottom left, you can see that is an image of URL files for 3 isolated dwarf galaxy pairs. So we had to download those for all of the 104 pairs. On the right, you can see that is a snippet of the code that I wrote for the subtractions after we reprojected. So why do we have to reproject these FITS files? Well, that is because all these FITS files were not exactly aligned when they were overlapped. We had to reproject them to align them to a chosen FITS file. For example, I chose to align them with the G FITS files, so they will all correspond to where the G image was located in DS9. So moreover, we worked with various AstroPy packages to edit FITS files and create the regions. So as you can see on the right, that is an example of the code that I had to create these regions for each of the galaxies. So we use SAO image DS9 to analyze each of the color subtractions and use Excel to keep track of the observations made. So at the bottom, that's a little snippet of my Excel sheet, which I kept my observations in. So what is SAO image DS9? It's Astronomical Imaging and Data Visualization Application. So basically, it's like Adobe or Preview, a program that looks at pictures, but this is designed to look at FITS files. Results. So colors are determined through the subtracting of UGRIS magnitudes. So the magnitudes subtracted in this research were G minus R, G minus I, R minus I, U minus G, and I minus Z. So on the right, you can see that these are from the isolated galaxy pair DM0087. So I have a frame for the ultraviolet, a frame for the green, and a frame for the U minus G. So if you look at that U minus G, the dark part represents the lower end of the subtraction. So that tells us that there is a low magnitude when these are subtracted. So the stars in this galaxy will be more on the blue end. So this is also for the isolated galaxy pair DM0087. So at the bottom I have the UGRIS. So there's one for the ultraviolet, green, red, infrared, and near infrared. So for the G minus R, we have a smaller value, and therefore the stars will have a color closer to the green range, same as the G minus I. In the R minus I, there is a larger positive value where you see those white areas. So that indicates that in that part, those would be more in the near infrared. So those stars at those little parts would be more in the infrared range. The U minus G. So just as before in the previous slide, we saw that that had a lower magnitude. So that tells us that those stars are going to be bluer in color. The I minus Z. So this also has smaller values. So these stars will be more in the infrared range. So as you can see, these are kind of scattered throughout. So in the middle, they're more of blue color stars, so therefore they're younger stars. And where you see in the R minus I, closer to the bottom of the region, those are more in the near infrared range, which tells us that those are older stars. So here is the galaxy non-isolated galaxy pair DM1503. So again, at the bottom we have the UGRIS images, so for the ultraviolet, green, red, infrared, and near infrared. So let's look at the G minus R. So in those white regions, those are more of the positive values, which indicates that those stars are in a range that is more in the red color. G minus I, same thing, they have positive values, so they're more in the red and in near infrared. Now let's look at the R minus I. We see that there is a large difference, which indicates that these stars are going to be more in the near infrared range. So the U minus G, those are smaller values, which tell us that they are not going to be in the blue range, which agrees with them being more in the near infrared range. I minus Z shows us that there's scattered positive and negative values, which tells us that they're going to be more in the infrared and near infrared range. So as we can see, these are going to be more in the near infrared range. So that tells us that these stars are going to be usually cooler and older stars. So as we compare that to the isolated case, the isolated case had more of younger, bluer stars, and then this non-isolated one, there's some younger stars, and there are also a lot more of older stars. So let's look at an example of isolated galaxy pair DM0052 and non-isolated galaxy pair DM1350. So these ones are at a larger separation. So in the isolated dwarf pair, it is clear that there are a bit more younger forms forming than in the non-isolated dwarf pair. But in both cases, at the separation, there's a lot less new star formation occurring than in the case where we had smaller radial separation. Although both of them do have some younger stars forming, it is clear that there are a lot more older stars. So this tells us that the star formation is very dependent on gravitational effects. So when they're closer together, there's usually more stars forming versus when they're further apart. Conclusions and future plans. Overall, it is clear that the star distribution in interacting dwarf galaxies are impacted. There are various factors that play a role in this, such as the separation and the distance from massive galaxies. So what I would like to do in the future is I would like to further examine the color maps created to determine temperature and mass of stars. I would like to contextualize results with other astronomical objects, and I would love to create maps of the temperature and mass distributions. Acknowledgements and work cited. So I would love to thank the Radford Office of Undergraduate Research and Scholarship, the Radford Physics Department, Dr. Liss, and the Summer Undergraduate Research Fellowship for giving me this opportunity to do research. Thank you so much.